Intermediate value theorem, very important theorem in calculus and very useful. Okay, so what is the statement? If a function f is continuous in the closed interval ab and fa not equal to fb, then f attains all the values between fa and fb in the interval ab. Okay, so here AB is a closed interval, means this is a real line and this is A and this is B. Means in this real line A less than B. So this is a closed interval. Since given function f is continuous in closed interval, so let us suppose there are two possibilities. One is this is x-axis and this is y-axis. So suppose this is a function fx of this type. Suppose this is A and this is B. Okay, so since A is here, so this is fa. Okay, so coordinate of this point is A, fa, and since this is B, so coordinate of this point is B and FB. Okay, B and FB. So since this function f is continuous, means this is y is equal to fx. This function is continuous in closed interval AB. Okay, and fa is not equal to fb. Second case, this is, it may be this type, either this is this type. So suppose this is A, so this is fa, okay, and suppose this is B, so this is fb, okay. So coordinate of this point is B, FB, and here A, FA. So either this type or this type. Okay, so here this function is continuous between A and B, continuous in A and B. Okay, so let k is a number between fa and fb, means fa less than k less than fb. It means between fa and fb, k is any number. Okay, so let us consider, now we consider the following function in terms of k. Okay, it means capital fx is equal to fx minus k. Since this function fx is continuous in closed interval ab, since fx is continuous in closed interval AB, and here capital Fx is sum of this thing. Since this is constant, so this is constant function is also continuous. Therefore, capital Fx is also continuous. Okay. Therefore, capital Fx is also continuous in closed interval AB. Now f of a, so f of a is equal to small fa minus k, small fa minus k. It is clear this is negative because this is fx. Okay, this is A and this is B. So K minus FA minus K, FA minus K. So this is FA and this is K. K is lying between this thing. So FA minus K is less than 0. Okay. And similarly, FV is equal to FB minus K. And this is greater than 0. Okay. It means FA less than K and FB greater than K. Okay. Here FA is less than K, FB greater than K. It means these are opposite sign. Okay. Thus FA and FB have opposite signs and Fx is continuous on closed interval AB, hence by Bolzano's theorem a point x equal to C of AB exists at which Fx equal to 0. Okay. Therefore, f of C equal to K means since f of x equal to Fx minus K and f of C is equal to 0, f of x is equal to 0 means fx minus k is equal to 0. So at x is equal to k, if c is equal to this thing equal to 0, it means fc is equal to k. Since k is arbitrary, so number of elements lying between fa and fv. Okay. Let k be number between fa and fb. Okay, that is fa less than k less than fb. Okay, now let us consider a new function capital Fx on closed interval AB, means capital Fx is equal to small fx minus k. Okay, since this function fx is continuous in closed interval AB and k is constant, constant function is also continuous, therefore capital Fx is also continuous in closed interval AB. Okay, so since Fx is continuous in closed interval AB, therefore capital Fx is also continuous in closed interval AB. Okay, now capital Fa. So what is capital Fa? So this is equal to Fa minus k. This is less than 0 since Fa less than k. From here, since Fa less than k, so Fa minus k less than 0 and f of b. F of b is equal to Fb minus k. This is greater than 0 since k less than Fb, so Fb greater than k. Therefore, Fb is equal to fb minus k greater than 0. Okay. Thus, fa and f of b have opposite sign and fx is continuous on closed interval AB. Hence, by Bolzano theorem, a point x is equal to c on closed interval AB exists at which f of c equal to 0. Okay, therefore from first, if we put f of c is equal to 0, so we get small fc minus k is equal to 0. Okay, therefore from first f of c minus k equal to 0, it means f of c is equal to k. Since k is arbitrary, which lying between fa and fb, it follows, it means the function f assumed the values between fa and fb in closed interval AB. Okay, it means there are two possibilities. So this is lying between this type. So k is either this. Okay, so there are at least one point. So in this function, at least here or here, so many values exist. Borel theorem, very important theorem in calculus, Borel theorem. Okay, so what is the statement? The statement is that if f is continuous function, if f is a continuous function on the closed interval AB, okay, let f is a continuous function on the closed interval AB, then this interval AB, then this interval AB can be divided into a finite number of parts, finite number of subintervals. Okay, such that for a given positive real number epsilon, such that f of x1 minus fx2 less than epsilon, where x1 and x2 belongs to AB. Okay, means x1, x2 belongs to AB. So it means let this is a function y is equal to fx. This function is continuous in closed interval AB. What is closed interval? We have, this is a closed interval. In closed interval, endpoints included. It means this is a real line. A and B belongs to R. So this is a closed interval. This interval can be divided into finite number of parts. Suppose x1, x2, x3 up to so on. Okay. And this is a function. Y is equal to fx is a function. Okay. So the Borel theorem states that if this function is continuous on this interval AB, then this AB can be divided into finite number of parts. In other words, this can be divided into subintervals x1, x2, x2, x3 up to so on. Then this fx1 minus fx2 mod of fx minus fx2 less than epsilon, okay, means this is fx1 and this is fx2. And similarly, for any 2 points between A and B, this condition satisfied. Okay, so this is the Borel theorem for continuous functions. Now, I am going to explain very important theorem, boundedness theorem. So what is boundedness theorem? Boundedness theorem on continuous functions. So if a function fx is continuous on closed interval AB, then it is bounded on AB. Okay, it means, let us suppose this is a function y is equal to fx. This is a continuous function on closed interval AB. Okay, then this is clear that this is bounded. Okay, so now I am going to prove of this very important theorem, boundedness theorem. So as we know, by Borel theorem, if a function is continuous on a closed interval AB, then this closed interval AB can be divided into finite number of subintervals. Okay, it means this is a Borel theorem. Means if a function is continuous on closed interval AB, then this interval AB can be divided into finite number of subintervals such that mod of fx1 minus fx2 less than epsilon, x1, x2 belongs to AB. Okay, so we shall use this theorem to prove of boundedness theorem. Okay, so now we have by Borel theorem we can divide this closed interval AB into n subintervals. Okay, means this is closed interval AB, so we divide it into A1, A1, A2, A2, A3, this type. So n number of subintervals means A1, A1, A2, A2, A3 up to an minus 1, an is nothing but B. Okay, then we have by Borel theorem mod of fx1 minus fx2 less than epsilon, where x1, x2 belongs to AB, and this epsilon is positive real number and epsilon greater than 0. So now we shall use this Borel theorem for first interval. Okay, so now for the first interval A1 fx minus fa less than epsilon for every x belongs to a1. Okay. Also we have, since mod of x minus y less than epsilon implies y minus epsilon less than x less than y plus epsilon. Okay, this is the property of modulus, because mod x is equal to x and minus x. So by this property we have y minus epsilon less than x less than y plus epsilon. It means this is x, this is y. So mod of x minus y less than epsilon, it means f of a minus epsilon less than fx less than f a plus epsilon. Okay. Now for the second interval, means a1 a2. Now for the second interval, a1 a2, by using the Borel theorem we have fx minus f a1 less than epsilon for every x belongs to a1 a2. Okay, so this can be written as also f of x minus f of a is equal to mod of fx minus fa1 plus fa1 minus fa. Okay, means by adding fa1 and subtracting fa1, this thing. Also by the property of mod of x plus y less or equal to mod x plus mod y. Okay, so here this is x, this is y, so mod of fx minus fa less or equal to mod fx minus fa1 plus mod fa1 minus fa. Okay, now here since fx minus fa, x belong to a1, or so by putting a1, so fa1 minus fa less than epsilon, so we shall use here this is less than epsilon plus epsilon is equal to 2 epsilon. Okay, it means mod fx minus fa less than 2 epsilon. Similarly, here we have used this property mod x minus y less than epsilon, so y minus epsilon less than x less than y plus epsilon. So by using this property here, so this implies f of a minus 2 epsilon less than fx less than fa plus 2 epsilon for every x belongs to a1 a2. Continuing this process, means for third interval and then fourth interval and then nth interval, so we get fx minus, so if we put here fa minus n epsilon, okay, so f of a minus n epsilon less than less than fx less than fa plus n epsilon. It means if we put in place of 2 is n, so this is fa minus n epsilon less than fx less than fa plus n epsilon. Okay, for every x belongs to AB. It means this is the form of L less than fx less than u. It means L less than fx less than u, which is condition of bounded function. Okay, therefore fx is bounded on AB and hence proved.